right. Oh, seniors, if anybody has a equation sheet that they want to give me by the end of the hour, is like, I kind of need it by then. So if you have an equation sheet and you still want to turn that in, I'll still take it before the end of the hour. Juniors, we'll start with some questions from chapter 15 up. I think problem set wise, we've done up through 70. I think we've done assigned up through 98. So if you guys have any problem set questions, I'd be happy to knock some of those guys out for you. Serge?
Is that one we were doing earlier? It was 92.
92. Sure. All right, 92. So we're condensing here. The order that I apply properties for condensing is power, product, then quotient. So I see two power properties because of the coefficients. The thing I have to be careful about here when doing this is remember that the power property applies to everything inside the logarithm. So I have like the exponent of an exponent things going. Next thing up, I'm going to be looking for product properties. I see the addition symbol, so there is a product property going on here. I'm going to simplify the parenthesis while I do that. And then I just combine my like terms with the y's, and I'm donezos. John?
You have power with power.
Correct, yeah, correct. Jack, Jacob.
When you have a problem like 87, or it's a fraction first, then you turn that into a power. Do you want to turn? Are we supposed to turn it to the first rate?
Yeah, typically the standard would be like whole number, positive whole number exponents would be considered fully simplified.
Okay.
So like rather than writing as a 1/3, write as a cube root.
Okay.
It's kind of the standard, although it's not incorrect to leave it as a 1/3. Particularly since the directions aren't like super specific as to what the final form should look like. Others. Yeah, Max.
Did you do 82?
82, sure. So here we're expanding. So for expanding, the rule or the order is opposite. So we're going to go quotient, product, power. So I do see a quotient property because I have two things divided. So I'll have log of the numerator minus log of the denominator. Next thing I look for is product properties. I don't see any of those. The last thing I'm going to look for is power properties. I do see that. I remember that a cube root is the same thing as a 1/3 power, a la Jacob's previous question. So that's as far as I could go there. Cool. Others. Jacob.
Can you do 29?
Sure. Okay. It says that the year 2000 population of Jacksonville, Florida was 736,000, was increasing at a rate of 1.49% per year. At that rate, what year would the population reach 1 million? So the model that I'd be using is that population model. So that's my model. And then I'm going to be solving this for t because it's asking in what year, like how long. So that's what the equation I'll be solving. At this point, we're doing these in our calculator. So put on my y equals menu. That's too many zeros. There we go. 7, 3, 6, 1, 2, 3. Why don't I write 500,000, Jacob? I think it said 1 million, right? Hey, it would have been no answer there, right? 1, 2, 3, 1, 2, 3. Okay, that's more like it. There we go. And we'll go to our window. I don't really know how long this is going to take. 100 years is probably appropriate, though. The y minimum, well, the minimum value this is going to have is that 736. So I'll just make a nice round 700,000. My upper bound is 1 million. I like to go a little bit more than 1 million, so I'll do like 1.25 million because I don't like having the line at the very top of my viewing window. And I don't know, go by 100,000s or something. So there we go. There's my 1 million line. Here's my population curve. Ooh, Jacksonville is going to be a regular old metropolis here. Second trace, intersect command, enter, enter, enter. 20.73 years. Or I would say during the year 2020. I think it asks for what year. Is that cool with you?
I know, you want round up, right? You want to say like 2021?
Well, it says in what year, so it would have been during the year 2020, right? If the question said like at the start of what year, then it would be round up to 2021, regardless of what the decimal point was, right? So it just kind of depends on the wording there. This one, not so picky. Anybody else? Happy to do some more if there's some more. John.
I understand this from the last problem that I think I understood how to do the question. But it might have been a problem like calculator. It was 15.
Okay.
And when I graphed the given function, it showed up as like a straight line on the x-axis, and I made the window really big as well.
Okay. Sure. So this is probably my suspicion as to what your issue was. So it says the population P in millions of people. So when will the population be 10 million? The equation I'm going to be solving for is this. I'm suspecting you put 10 million there, and this thing is just growing so slowly in that regard, it's like not really conceivably going to get to 10 million. Yeah, especially since the upper bound is 12.7, since it's a logistic. It's not going to grow indefinitely. So I'm guessing that was probably the issue. Okay, yeah. It's one of those careful, like, reading comprehension, it got me. Taylor.
Can you do 6 tabs? Just skim over it.
Yeah. So it says the population P in millions of people of New York State T years after 1800 is modeled by the equation yada yada. So what is the population in 1850? Well, there the T is just 50, right? So I'm just plugging 50 in for T. Is that cool? For this one, the year is 2010. How many years after 1800 is that? 210. So that's my t there. And then the maximum population, well, I noticed that this is a logistic function. So the upper bound for a logistic function is just going to be whatever the value's in the numerator there.
So is this like the last one where like for A, I got like 1 point something?
Yeah, that's right. 1.79 million.
Okay.
Right, because it says the P of T that you're getting is in millions of people.
Okay, because that was throwing me off. Because I guess I didn't read it like that. So when I got 1.79, I was like, that does not make any sense.
Nope, 1.79 million
Okay.
in 1800 is probably reasonable for the state of New York. It's a lot of people in 1800s United States, you know. You're just a few years after signing the Declaration of Independence. You only got 13 colonies or whatever, probably rattling around. I don't know. U.S. history people, when did they start adding new states? After the first 13. Yeah, I don't know. Yeah. Anyways, but sounds like you were doing the right thing. 179, I think, is the correct answer for part A. Just million. Not 1.79 people. That'd be a weird result. There's a 1.79 people in the state? Get out of town here. I mean, at one point that was probably true if you're not counting the Native Americans. 1.79, non-indigenous peoples. Okay, we feel good? Yeah, go ahead, Tay. Sure, 36. Okay. So the population of deer T years in a state park modeled by the function yada yada yada. Initial means what time? 0. So I just plug 0 in for T. If I do that, it's like, what is it? It's 1001 over 91, whatever that comes out to be, like 16 or something maybe. Let's check. Oops, 1001 divided by 91. 11. When will the number of deer be 600? So there I'm just going to be solving that equation, right? Whatever that comes out to be. And the maximum number of deer in the park is just going to be the upper bound there. I feel good? You don't need me to solve the solver?
No, I just need to make sure that I was doing it.
Yeah, totally cool. Be sure. Not a big deal. I just want to make sure I'm giving you what you needed.
Yeah.
Since I just kind of hand waved at like the setups here. Didn't really do anything. But it's part of it, it's who you're talking to, where it's like just the setup is probably enough. You don't need the details. You're not a details, so you can handle the details yourself, person. Yeah. Because you're pretty good at math. I think I'm a fair judge of it. You know, you're better than I was at the same age.
I feel like you would be one of those kids that was like always really good at math. Like when everyone else was adding it to figure out and you were one like,
Yeah, we got Jimmy Neutron.
No. All right. I'm not joking. I'm not just flattering you for the sake of flattering you. It's true. We good then? Ready to move forward?
Wait.
Are we doing a lecture first and then a quiz?
Yeah, of course. We always do the lecture before the quiz.
It's like it's in our heads now.
But here's the reason why. Because somebody takes 5 minutes on the quiz, somebody takes 25 minutes on the quiz.
That might be the second one.
What do the person that takes 5 minutes on the quiz do? Sit there and do nothing. If we do the lecture first, they have something to do afterwards. That's why we do it in that order. And that way, also, I can stop the lecture when I need to, if it's running longer than I expected, and we still have time for the quiz. If we go to the quiz and it just goes forever, or I have to cut it off, I have like a hard cutoff where it's like, no matter where you're at on this, you know, you're done now because we have to move forward, you know? It's a little nicer, or I don't have to be mean doing it the other way. You know, or of doing it this way. If I do it the other way, I might have to be mean. And I don't want to have to be mean. Not that I'm afraid to be mean, but it's like, you know, I'm just going to arrange the course in such a way that I don't have to. Because I've been doing this long enough to go, oh, look at this. There's a smart way to do this and a dumb way to do this. Or at least like a, you know, like one that potential problems can arise and then one where really no problems can arise. Other than you don't necessarily like the order I do it in. But, you know, when I explain it, usually they're like, oh.
Yeah.
Yep. All right, I get that. All right. Section 15.4. We're finally done dancing around the possibility of using logs to solve things. So this section is all about solving exponential logarithmic equations. It'll take 2 days to do this section. The first day we're just going to do like numeric examples, and the second day we'll do some like application examples where we have some story problems and stuff going on. Okay? So the first day, or first idea here, is we're going to take advantage of this one-to-one property. So what this is saying is, if we have any exponential function, if b of x, or b to the x, is equal to b to the y, then x has to equal y. Right? If 2 to the third equals 2 to the x, x is 3, right? And then we can say the same thing for logs. So if I have log of x equals log of y, well, then just x has to equal y. Do this preemptively because I have a feeling it's probably getting close to that lunchtime break that everybody comes storming through the halls like a herd of wild animals. All right, so these are the two major ideas. There's a couple of different ways you can kind of interpret this. When we do the actual examples here in a moment, we'll kind of talk about like, okay, if you think about it this way, you can do it this way. If you want to think about it that way, you could do it this way. They're both, you're accomplishing the same thing. It's really the same set of steps. It's just a matter of like, how do you best understand things? So let's do some examples. Solve for x. Oops, actually I want to do this one first. All right, so let's say we have 12 times 3 over 2 to the x over 5 power equals 27. First thing I'd want to do, standard solving procedure. Not a great sign, guys. Lily,
Divide 26 by 12.
let's divide both sides by 12. All right?
Wait, could you use the, what was it called, quotient property?
Quotient property works for logs.
Logs. Okay. Do the log both sides. Yeah.
You would not want to do the log of both sides yet
Okay.
because you don't have the exponential isolated.
How can I use the quotient property?
You cannot. Well, I mean, like, I guess you could, but like, why? Okay.
Oh, by the way.
Oh, yeah, that's not right. That's 9 over 4. Sorry. It's like 9 is definitely not right. 9 over 4, though, that looks much nicer. Okay. Now what? John? It's time.
It's time to take the log of both sides.
Yeah. So you can think about it that way, or the alternative would be trying to use the one-to-one property. So if we tried to use the one-to-one property instead, what we'd want to do is find a way to rewrite 9 over 4 as a power of 3 over 2. Sometimes that's really obvious, like it is in this case. 9 over 4 is 3 over 2 squared. And then you can just use that one-to-one property, and we get 10. The other approach would be to take the log of both sides, as John suggested. Which log of which base would we want to use? What base would we want to use for that logarithm? I would not use x over 5. You definitely don't want a variable in the base of your log. 3 over 2 would be a good one to use. Typically, you'd want to choose a log whose base matches the base of your logarithm. That makes it algebraically as simple as you can, or as simple as things can be. Everybody's cool with what I've written there? Wroten. Kind of English am I speaking? It's worth pointing out that log base 3 over 2 of 9 over 4, you could do by hand if you wanted to, but unlikely that if you chose to go this route, you would have recognized that. Okay, last step would be to multiply both sides by 5, and then just type this junk into our calculator. When you do that, you should get 10. Reminder again, to type a log of any base, you press the math button, you scroll down to the bottom, you pick the log base command, and then you type it in exactly like it looks like on your sheet of paper. John?
How did you get the last step in the red?
Uh-huh.
Step on that.
So the logarithm cancels with the exponent base. So you're left with the exponent equals the right-hand side.
Okay. But the base is the same as the input.
Yeah. Log base b cancels exponent base b. That was one of the properties that we came up with on, oops, I guess not this day, the previous day. Where was it? Right here in the yellow. Right? We identified that a couple days ago. That's the property that I took advantage of there. The same thing is true with exponent base in a logarithm, right? I can use the exponent base to cancel out a logarithm using the same kind of method. Is that cool?
Yeah.
All right. You buy that. It's like, oh, I guess we did do that. And you didn't make anything up here. It's something you told me about before that I just didn't remember, which is cool. You know, like, ask your questions. Right? A bunch of little Fonzies in here. The Fonz was a character on a show called Happy Days that aired in like the 60s and 70s. It was about like 50s America. And the Fonz was like literally the coolest person in the country for like a decade. Henry Winkler was the actor. He's the coach in The Water Boy. If you believe that he was like the coolest person in America. Yeah. Yeah. So you know the phrase jump the shark? Have you heard that before? So that's a phrase that like when a TV show or movie or whatever starts to stretch credulity, like it's like, okay, this is now getting like too unrealistic for me to kind of believe this story anymore. I'm kind of out on this. Comes from the show Happy Days in an episode where the Fonzie was water skiing and literally jumped over a shark on the show. Because he's the Fonz. Anyways, example B, that's enough TV trivia for today. What should we do first here? Good, divide by 14. So when I do that, I get 9. Now this time, if I try to use that one-to-one property, it's a little less obvious how to write 9 as a power of 1/3. Anybody see it? -2. The negative makes the reciprocal, and then 3 squared is 9. A little bit harder to see that one. So the negative sign makes a reciprocal, so 1/3 would become 3, and then it's squared. 3 squared is 9. Or if you're like, oh boy, I don't know if I would have saw that one. What else could you do? Do the log of both sides. Which log would you want to use in this case? Log base 1/3. And then we'll add 1 to both sides. And if I type that into my calculator, I'm going to get -1, just like I did doing it the other way. But let's show you. Ooh, Boise, what did I just do? Sorry for anybody getting motion sick watching me scroll around through that at high speeds. Does that ever happen to you? Like if you're watching somebody else play on their phone, you ever get kind of like motion sick as they're scrolling through things faster than you'd like to scroll through? No? Happens to me when my wife wants to show me something on the internet on her phone. I'm just like, ooh, you're going so fast. They didn't even get a chance to look at any of these things. Jacob.
So we're on a test and you give us that problem. Is there a preferred way that you want us to solve it?
Nope. In fact, they're doing identically the same thing. So it's just a question of like, what notation do you feel more comfortable with? So far, pretty easy so far, right? Not a big deal. And you got to be thinking in your head like, oh, Mr. Kulik, things have to be getting harder soon. Sure, this is probably as hard as I would expect you to deal with as far as a exponential equation would be, or hard as I would make an exponential equation. So when you look at this, there's probably like 3 things right off the bat that you're like, this makes things a lot harder. What are some of those things that you notice about this equation that wasn't true about the other ones that are going to make this a little bit more complicated? We got x's in 2 different locations. That's the big one. Yep. What else? Got a fraction, and negative exponent would be what I would say. So we have a negative in the exponent. I have 3 to the x plus 3 to the negative x. Those are all 3s.
Oh.
I can see that.
Yeah, man, my penmanship's crummy, you know. I get it. All right, which one of those 3 things do you want to take care of first? The fraction, great. How are we going to do that? Multiply both sides by 4. That's pretty easy and hopefully pretty obvious. So get me that one-way ticket out of fraction town there. All right. Next thing we'll do is we'll worry about the negative exponent. How do you want to take care of that? 1 over 3 to the x. What's the problem with doing that? So you're back to fraction town again. We just left. I don't want to go back. What could I do instead? I'm going to multiply both sides by 3 to the x. Why would that be helpful here? So I distribute the 3 to the x through. Oops. So when I have an exponent times an exponent where the bases are the same, we add the exponents. So see you later, negative exponent. Get out of here. Notice that we did not enter fraction town at any point there. I'm leaving this town. I'm never coming back. That's a lie. Fraction town's not that bad.
Mr. Cook, do you have a key to Mr. Fazzini's room right there? Borrow for 2 seconds.
You mean Miss Garcia's room?
Yeah.
Yeah.
My bag in there. Thank you.
You're welcome. Is it your lunch?
It is my clothes, actually.
Oh. Seems like he was still wearing clothes. I'm confused. Maybe he borrowed them? It's weird to come to school without your clothes on, though. Happens to everybody? Okay, no follow-ups. All right. So what should we do next? We still got those x's in 2 different places, right? Well, my recommendation to you would be to move it on to this, everything onto the same side. And this should remind you of something. What does this equation kind of look like?
Cool, thank you.
No problem, homie. Did you lock it back?
I did, actually.
Okay. What does that remind you of? What kind of equation have we solved before that has 3 terms in it like that? Quadratic. What if I said this was in the quadratic form? Are you not convinced? Let me convince you. So remember that when we have an exponent of an exponent, we multiply, right? So I can take 3 to the 2x and think about it as 3 to the x squared. You buy that? Well, 2 times x would be the same thing as to the x squared, right? That's an exponent property from last year. Yeah, that's an oldie, but it's a goodie. All right. Still not convinced? What if we replace the 3 to the x's with y's? Woo! Looks pretty quadratic to me now, which is great because we know how to solve quadratics when we have variables in 2 different locations. Not a big deal. What are the 2 major methods we use to solve quadratics? Quadratic equation and factoring. Which one would I use here? There's 2 numbers that you know to multiply to give you 1 and add to give you -8. I don't know those 2 numbers either off the top of my head. I think I'll use the quadratic formula here. Yeah, no problem. Again, it's been a while since you've solved a quadratic or had to factor something. You know? We can be, you know, a little uncertain of what to do. So there's the quadratic formula. You guys all have that memorized, right? -b plus or minus square root b squared minus 4ac all over 2a. Okay. So I have 8 plus or minus -8 squared is 64 minus 4 is 60. And the square root of 60 is, what, 4 times 15? Why would that be important? Because the square root of 60 would then be the square root of 4, 2 times the square root of 15. Just simplifying. 60 is 4 times 15. Square root of 60, square root of 4 times square root of 15. Square root of 4 is 2. And so I could reduce that then to just be 4 plus or minus square root 15. Am I done? No, we're not done. Why? Yeah, we've solved for y. What do we really want to solve for? We want to solve for x. So I'm going to write this as 2 separate equations here. Everybody's still doing okay? All right, how do you want to solve this equation? John, log of both sides. Fantastic. Which log should I use? Log base 3. I want it to match the base of my exponential. And I only want that because it makes the solving the easiest. You could use any log here, but like it gets kind of yucky if if you just do any old log. So when I type that into my calculator, I get about 1.88. If you're wondering how I did that in my head, I didn't. I've just done this problem, I don't know, 6 times now in the past couple of weeks, so I just remembered what the answer was. No good reason why I would have remembered that or would have known that otherwise. It's not like I was doing some crazy mental math you're not used to. What if we wanted to try to do this the other way? What if we had wanted to try to rewrite this using like the one-to-one property? How could I rewrite 4 plus the square root of 15 as a power of 3? Is that something that's realistic to do? Sure it is. the exponent is just log base 3 of 4 plus the square root of infinity. That's what it would be. So you see really quickly that we're doing the same thing, whether you want to use that one-to-one property or you want to think about taking the log of both sides. You are doing the exact same thing. Sergio. Sure. So that's just like a hypothetical there. That's not really necessary part of the solving piece. And for the other one, we do the same thing, right? All right, how many answers did I get here? 2. Am I always going to get 2? Sure, come on in. Stapler up and hand her to me. Well, I always get 2 answers. No, okay, great. Why not? What? Possible to have 0 answers or the numbers? Well, x equals 0 would be fine. Okay. So there's 2 things that could happen. When we're solving the quadratic part, how many answers does the quadratic give us? Right. 0, 1, or 2 answers. So you could get less than 2 answers just because the quadratic gives you less than 2 answers. But there's another place that we could lose answers. Let's say we did get 2 answers from the quadratic. I could still get 0, 1, or 2 answers total. Where would I be losing answers at, possibly? Lily?
Inside the logs negative.
Yeah, so if those answers to the quadratic were not positive numbers, if they were 0 or negative, when I went to take the log of it, it would be an error. I couldn't get a solution from that. Okay, so there's a couple of places where I have to be a little bit careful, where you may not be getting the 2 solutions that maybe you expect based on this example. Is everybody okay with that idea? Alrighty then. Let's go to another one. This time we're going to look at a logarithmic example. So here's a logarithmic equation. So what's the first thing y'all want to do to solve this bad mama jamma? I would divide by 3. Very good. Again, my goal would be to get the logarithm part all by itself before I do anything else. Okay, now what? What? Oh, no, I would not do that.
Well, wait.
I would not, in general, when doing a logarithmic equation like this, expanding is a bad idea. Okay? We'll see later in an example where condensing is a good idea, but in general, expanding can get you into trouble. You can, but I wouldn't do it here. Lily.
Go back to exponents. Like I remove the log. So 10 squared equals x squared.
Okay, so you could use our definition of a logarithm, and that would give us 10 squared equals x squared. You definitely could do that, in which case x would be plus or minus 10, right? Okay, what else could we do here? I could use the one-to-one property. So how do I rewrite 2 as a log 10 number? Well, it would be log base 10 of 10 to the second, right? And then from there, we could do that. And get the same thing. The last thing we could do is try to cancel the logarithm. So what's going to cancel out a logarithm? An exponent base. Which exponent base would I use? 10. Why 10? It matches the base of the logarithm. So again, I try to write those exponent bases big so that it doesn't look like I'm multiplying by 10. So either of the ways I'm doing this, I'm going to get the same thing, right? Everybody cool? What would I want to be? Oh, hold on one second. Am I done? Is the problem over? Have I finished it? Yeah, so every logarithmic equation I have to check because I can get extraneous solutions. Okay, the check is very easy though. All I need to do is make sure when I plug my answer back into the original equation that I'm not therefore taking the log of a non-positive number. So if I plugged positive 10 in, well, positive 10 squared is positive, so we're good. Positive 10 is fine. If I plug negative 10 in, negative 10 squared is positive, so that's fine. So both answers are acceptable. You could check to make sure that both sides are equal, but that's a little bit more checking than you really need to do. All we really need is to make sure we're not taking the log of a negative or 0. We just have to make sure we're getting positives during our check. John.
Even, if the exponent is even, does that always guarantee that it will come out with a positive number, and if it's odd?
Well, I'm confused that I see what you're. What's it?
If the exponent is even,
Uh-huh.
it will always be a positive. It will always
No, what's that it? The solution?
wait.
Is that what you're asking?
Because I don't know what age.
Okay.
If the exponent is even,
Mm-hmm. You said then will it?
then will it.
What's
yes,
it?
Will the answer, or will the log of whatever's in parentheses, that number will always be positive.
Nope.
No?
Logs can give you negative value. That's okay.
The input.
Sure.
Oh, I thought that was
Well, because if it's squared,
right, but if you have x to the third and our answer is negative 10.
right, then you would your answer would be extraneous.
Right, that's what yeah.
That can happen.
That's what that
So in that case, you'd have no solution.
yeah, you'd have no
Right.
so
That's why you have to check.
yeah.
Because you can get an answer that seems there's nothing illegal algebraic that we did, but it just doesn't satisfy, the actual equation. Is that okay? Okay. I want to point out that the reason, I think John or Luke, one of you two suggested to use the power property here. I want to point out why that's a bad idea. If we do the power property, we lost the solution. Okay. Because we no longer had an x squared, so we don't get a plus or minus.
There's like no error.
So you're right. There isn't an error, but the issue is that, like, if you try to expand a logarithm to do the solving, this kind of thing can happen where you end up losing solutions, which stinks, which is why I told you, like, you don't want to do that. And it has to do with, like, it's kind of a theoretical kind of argument that has to do with, like, you're moving between, so, like, you're taking something from, like, this set, and you're mapping it with a logarithm to something on this set, right? So you're taking a number between 0 and infinity, and the output can be any real number. So to go backwards, if we have some, you know, like, you can end up pulling something from here that forces us to get an answer not from over there. That's these extraneous solutions. It's a complicated argument. The thing that you really want to have is just, like, don't expand your logarithms when you're solving. Take that. Okay, just take that. We'll just go with that. Like, I wasn't prepared to make this argument, so it's going to be kind of unsatisfying because I'm going to stumble my way through it. But it's one of those things, like, I wasn't expecting anybody to mention that. And it's like, oh yeah, that's not a unreasonable idea, but it's a bad one. And seeing why it's a bad idea is kind of tough. And I would say, John, even in some, it wouldn't even be a bad idea in all situations, but that particular problem was absolutely a bad idea. For the reason we just showed, is that you end up losing a solution there. All right. Last example, and we're going to be done. We'll take the homework quiz after we finish this one. So this one, oh boy, looks a little bit tougher than the previous one. What do you see that's different about this one and the previous one? We got x's in more than one location, and we got a bunch of logs here. Instead of just one log, we have 3 different logs, right? And each of them have an x in it, which is the bigger problem. What should we do? What's the first thing to do here? Yeah, you'd want to condense this. So look at the left-hand side. What could we do to the left-hand side? And by power, you mean product.
Oh, yeah.
I knew. And on the right-hand side, what can we do? That one's a power. Everybody happy with what we did? What should I do next? Serge.
I just have a quick question.
Yeah, what's up?
So when you condense, it goes power, product, quotient, and then it's just vice versa for
Yes. Well, I mean, yeah, we're going to FOIL eventually. I would use the one-to-one property. What's that mean that I can do? Yeah, you can just drop the logs out of there. I'm going to FOIL at the same time. So, Luke, whether you FOILed first and then drop the logs, or if you drop the logs and then FOIL, or you just do it both at the same thing. Yes, eventually we're going to need to do that, for sure. When you want to do it is, flexible. All right, what do we have now? Quadratic. What should I do first to solve this bad boy? Got to be equal to 0. So if we just subtract the x squared from both sides. Okay. And how do you want to solve this quadratic? Yeah, you could factor it also. This one actually is factorable, but since the leading coefficient isn't 1, you'd have to do like that longer factor by grouping method, which, it's not always obvious if it's going to be factorable anyway, straight from the get-go, and like the method is probably just as long as using the quadratic formula. So like, why would I do it? But you could. 5 squared is 25, minus 16 is 9. The square root of 9 is 3. 5 plus 3 over 4 is 8 over 4, or 2. 5 minus 3 over 4 is negative 2 over 4. I'm sorry, it's positive 2 over 4, or 1/2. So I'm done, right? No! What do I still need to do? You gotta check. So I'm going to take the x equals 2 back to the original equation. 3x times 2 minus 2 is positive. Don't care what it is, just has to be positive. 2 minus 1, positive. 2, positive. Looks good. Let's do a half. 3 times a half minus 2 is not positive. We're done checking. That is an extraneous answer. We do not count it. We have one solution. That solution is 2. Cool with that? Alrighty. At this point, you guys can do up to 130. And you guys put your stuffs away and we'll get this homework quiz done, Roonies.